This program is brought to you by Stanford University. Please visit us at stanford.edu.
This presentation is delivered by the Stanford Center for Professional Development, providing graduate-level education to working professionals, online, on campus, and on-site. For more information, please visit study.stanford.edu.
Today we're very pleased to have Jay Misra from the University of Texas at Austin. He's going to be talking about, well, the title has changed a little bit, structured concurrent programming, and the work that he's been doing there. Jay, I'm just going to pass it on to you. I think we need to get going here. Thank you.
I teach a class at around this time, and I found that they all fall asleep in about 30 minutes. 20% of the class is asleep in the first 5 minutes, no matter what I say. So the solution I have found is that you ask me questions during the talk. So it's completely free. Feel free, just put up your hand, ask me questions. And if I'm not getting enough questions, then I'll ask questions. So what I'm going to talk about today has a lot of philosophy and such things, and I'll skip over all that. Let's go to an extremely concrete problem. The problem is the following. Let's say I have two preferred airlines, let's say American and Delta, and to come here, I would like to buy a ticket. And this is how I would like to go about it on a website or somewhere. I would contact the two airlines simultaneously for price quotes, and if either of them quotes me a price less than $300, I'll just buy it without waiting for the other. However, if that's more than 300, I'll wait for about 10 minutes, and by then if the other one has come through, I'll buy the cheaper ticket no matter what it is. And if only one quote has come in, I'll just accept that quote, and if neither has come in, I would like to get some indication that I didn't receive a response. Now this is a totally trivial programming problem, but I started doing it actually on a computer, make requests to those sites, and actually write the program, and it's extremely difficult. I don't understand why it is so difficult. Some 10 years ago, I was the chairman of my department, and we had a person who was hired to take care of the visitors. Large number of visitors come in, they would like to give talks. So her job was to contact the visitor, get a particular date, and then find out, and then contact airlines just like that to find a good price, then contact hotels, then get a reservation, and then send a message to our audiovisual people to make the room ready and check the room before the person comes, have someone pick him up at the airport. And we hired a person who didn't know all these things, and she found it very difficult to understand this. So once I had to sit down and actually write down the steps. If this happens, then do this. If this happens, then do this. Then contact this. And then I realized that what I'm doing there, or what this person would be doing, can be automated. Almost 95% of it is automatic. So why aren't we doing it? And that was very surprising to me. But lately, I have begun to realize that the World Wide Web will have large number of services. We'll have an extremely large number of services, and we should be able to exploit them by putting up some combination of the services to do something important, like this. This is a very small problem, and we should be able to program it very quickly and get something out of those services. So the kind of thing we would like to do are some of these. Get data from remote services, calculate with this data, and depending on their values, invoke yet other remote services, invoke alternate services for failure tolerance, and poll service, download, have a service call another service. So once I started writing them down, they were like 54 things, and then I saw that they're actually implemented, all 54 of them, one by one. You go to some kind of a business process execution language, and you will see them. So the challenge was, how can we simplify them? What are the major things and which are the minor ones that we don't need to worry about. If you think about it, there are really three kinds of things that are going on. The first is that somewhere you have to maintain databases. The airlines have to maintain their databases, and hotels have to maintain databases, and that's persistent storage management. And if you request some information from them, they will give you the information. Perhaps they will update their own database. This is an important question, but it can be handled. It's being handled, and this is not the problem that I'm going to solve. I'll just assume that databases are available. The second one is that there is sequential computational logic involved in some of the things I'm doing. Like you have to get a quote and compare it against $300 to see which one is higher. Or sometimes you may want to print out a number of items in alphabetical order, so you need to sort them. So these questions are pretty well understood by now, and this is not the problem I'm going to handle. What I would like to talk about is how do I orchestrate the computations? How do I say that start asking for quotes from two parties right away? As soon as one comes in, compare it, see if it is less than 300, and then do something and ignore the other one. If that's not the case, wait for both. So in some sense, it's a flow of calls, and I would like to specify this flow succinctly. So I designed a number of primitives, and the collection of primitives I call orc. Orc is the first few letters of orchestration, but I'm also told that it's the name of a horrible animal in some movie. I watched the movie several times, but I couldn't understand it. But a 6-year-old assures me that that's true. So, in this notation, you invoke services by calling them. And in order to have a neutral name, I introduce the term site. Site means it's some kind of service. So a site could, for instance, if you call it with a number, it might give you the square of that number. That's a site. Or if you call for a quotation from American Airlines, it might give you a quotation. That's a site. Or you send it a file, video file, and it sends you a compressed version of the video file. So it's reasonably functional in nature. Its goals are understood. It can sort, it can do things, but it's not into doing concurrent programming for you. The next thing I do is manage timeouts, priorities, and failures within this model without doing anything extra. There isn't any, yeah?
So all your examples of invoking a site just now were query operations. What about, for example, going back to your airlines, when you actually book, when somebody gives you an acceptable price quote, you actually book it, committing to pay the money?
Yes.
Is that also your model?
Yes, that will be a site. And that will be a site called a commit site of that airline. And you will have a pledge from the airline that if you commit to it by this date, they will actually hold the ticket for you. So this notation has only two ideas in it. You can only call sites, and you publish values. Just like when you evaluate an expression in, say, Java or something, it has one value. Here, you may have multiple values. And I'll explain to you what publication means. The important thing, and this came after a lot of work, is that it has only three main ideas, three combinators. And there was an explanation that was given by Shankar, who is here, that was very nice as to how to understand these combinators. And I don't believe I'll have time to describe the semantics, but I did find the semantics, when I managed to find a formal one, to be quite important. It actually clarified in my mind how to implement it efficiently, and we did implement it that way. So here is in one slide all of it. That's it. So if you understand the implication of that slide, you don't have to sit here. So the first one, in Orc we have expressions, and expressions come in two flavors. Either they're simple, atomic, or they're composed of two Orc expressions. The simple one is that you just call a site, call a service. You can give it parameters. So one example of that is you call the site CNN, and you give a parameter which is a date. And you expect that the service will return to you the news page for that date, whatever it is, in some form. So if CNN responds to you, whatever value it responds with is the value published by this expression. We of course expect that CNN may not respond to us, or may respond to us after such a long time we don't care. We'll keep that in mind. So unlike arithmetic expressions where you know that each term will be evaluated in time, there is no assumption here that CNN will respond. There are three ways to compose Orc expressions. The first one is that you have an expression f and g. You do them independently. Just do f and just do g. So f will require some number of side calls, or invoke some number of side calls, and g will invoke some number, and f will publish some number of values, and g will publish some number of values. So in particular, if you think of two services, CNN and BBC, just put a bar, CNN bar BBC, and you can see that we'll run two independent computations calling CNN and BBC, and we can perhaps publish even two values, or maybe one value, yes.
So does that statement finish when one of F or G finishes, or does
no,
it
we don't ever finish statements. We don't ever finish. We just keep them running. But after some time, of course, nothing will happen. So in particular, if I write CNN bar BBC, then if I publish two values, then nothing more will be done. I know that, right? CNN can publish at most one value. BBC can publish. There is no formal termination. So it just a thread runs to its end, and we just leave it there. The other two, the other operator is called piping, and the last one is asymmetric composition. Piping is that you have two expressions f and g, and f publishes some number of values, and for each value published by f, you create a copy of g and do it. So if f publishes two values, you will create two copies of g and do them. Each value published by f will be given the name x, and g has probably a formal parameter x inside it, so each copy will take that value of x and continue working. And the third one is very similar, except for some value, exactly one value of x, you will do g. But the semantics are slightly different, and I'll go into operational semantics in a second. And the last two, this interpretation for some and for all, that's due to Shankar. And that I like because it showed up in other ways how it's related to predicate calculus. So here is the first example, symmetric composition. And I already told you how it works. How long do we go till 5:15? 5:30. Okay. We don't have to go that long. No. So if you're all good boys and girls, then we can finish by 5. So if you were familiar with some other kinds of process calculi like CSP and CCS, there is no communication between f and g. They are totally independent. But of course, f could call a site, and g could call the same site, and that's how they could communicate. But that's outside our formal system.
Question?
Yeah.
Does that mean that formalism has no, within this formalism you cannot create sites?
Yes, actually you can. But that's probably the last thing that I'll show. I may not even show it. Yes, you can, and using that you can show that this is as powerful as some other formalisms like pi calculus. So we do allow sites to create sites, to return sites as values. So you might call a discovery site that give me the name of a site which provides this service, and then call that site. So in particular, an example of that is you can call a site called build a channel and return to me the name of the channel. And then both parties, f and g, could write into the channel. That's how they can communicate. So you get an extremely high amount of power, but you don't change the basic model.
What is the character of the published value?
Well, yes, good question. I'm not going to address that question. So just take a value as typical kinds of values, typical structures.
What does it belong to, though, when it's published?
What does it belong to? It's some typed value. but I'm not addressing the question of types.
But it's not a value returned by the...
It is a value returned by some site.
By some site.
Yes. It has to be a value returned by some site. So CNN you call, you get back something, that's a value that you publish.
Oh, I see.
Here, let's go a little bit more and it will become clearer. So the first example, you call CNN, and whatever it returns, you call it X, and you call then the site email with some address with X, and presumably email will send an email with that value, but it also returns or it responds with something. So email with respond, typically I expect it to respond with some termination signal. Yes, I have sent that mail. So the publication from that expression will be that signal. The value returned by CNN will not be seen. It's not a publication. It's consumed internally. The second example is more interesting. If you have CNN bar BBC, you can perhaps get two values, one from CNN, one from BBC, and for each one of them, you will send an email. So you may actually send two emails. So to understand piping, this picture is useful. No, this picture is useful. That at the top, F is in red. It's a thread that's running at the top. The graphics is horrible, but I hope you get the idea. And at the points where it meets with the blue line, that's where a value is published by F. And at that moment, a copy of G is created, and that copy runs independently of F. And so you have 3 copies of G running and 1 copy of F running. And it's quite possible that F may produce infinite number of values, and you will have an infinite number of copies. I'll try to make it so that you don't have to remember anything, but for the moment, just remember that bar has the lowest precedence in long expressions. I don't want to put too many parentheses, so that's how it stands. Okay, this is the last combinator where, and remember that we have 2 expressions F and G, and we expect to use at most 1 value from G. So you may believe that one of the ways to do it, one of the possible semantics of that would be to sort of start G, wait for the first value, and then start F. It turns out not to be a very good idea. And in fact, what Shankar had shown with the connection with predicate calculus, if you do that, then it breaks one of the rules of predicate calculus, that over a empty interval, for all and there exists should evaluate to different values. So piping and this become equal at that moment, and they evaluate to the same value. But besides that, I couldn't solve a number of problems. I couldn't in particular solve the airlines problem with that semantics. So the semantics that I've adopted is that we start F and G simultaneously, start evaluating them simultaneously. Now F, of course, may have mention of X. In particular, if you look at under the first bullet, suppose I have the expression M bar Nx, where X comes from G. If I start evaluating F, I can start evaluation of M part. I can call the site M, because that doesn't need X. But I can't call Nx. I need the value of X. So that particular call will be suspended. Simultaneously, G is running, and yeah.
So if it turns out that N was also 2 parallel processes, why couldn't you run parts of N as well?
N is not a parallel process, as I have shown it. N is a single thing. But yeah, it may have a fairly detailed structure. It's a tree structure. And you do as much as possible, but at some more points where X is needed, you will have to stop. Right? And G is running independently, and if it publishes a value, we'll call that X. And there are 2 things that will happen then. First, we kill G. We don't need G to run anymore. No more values are needed. So killing means we'll not call any more sites from G, nor publish any more values. So it's gone. And the value that G has produced, we call that X, and all the suspended calls can now proceed. So is there a question? So either, yeah.
There's no concept of timeliness.
or
There is-
timeouts?
Yes, there is. I know you. That's why I know you will ask that question. Yes, there is. So the first value will be used. I'm going to come to time in a second. And actually, not a second, two slides. And that's the whole theory. But in order to make things go, I needed a library of sites. And I need around 2 or 3 sites, definitely. Otherwise, I can't write any programs. The first site I need is 0. 0 is a site which never responds. That's surprising. Why do you need a 0 if it never responds? Very useful, because sometimes you want to cut off computations. You explicitly say, I want to cut this off. If is a site which accepts a Boolean argument true or false. If you give it true, then it responds with a signal. Signal is a unitary value. That's all there is to it. But if you give it false, it doesn't respond. So it sort of kills it off there. And signal is a site which returns a signal immediately. It's same as if true. And the last one is the timer. The timer site, I'm taking the argument to be integer. It returns a signal t time units later. I think in our implementation, the time units are 3 milliseconds. So if you give it 3, it will go for 3. If you give it 1,000, it will go for 3 seconds or something.
Automations from CSP?
Which ones?
Well, the whole mechanism of waiting for a value and timing out on the wait.
I am not sure how to do that with CSP alternation, because you need some properties of timer. Here, I need the signal to come exactly 2 units later. So, which is very difficult.
You need it to come within?
No, exactly
you need
2
it to come
units.
exactly to.
If it comes within, it's useless for timeouts.
Right.
And the way I implement that is for you to believe that this entire evaluation process of a program is done on one machine. And we're running the clock of that machine. And I've developed the theory that tells me when, under what circumstances, I can distribute the evaluation across many machines. Because sometimes the timer isn't needed. In fact, that's done automatically. So let's write some programs. So this is a centralized execution model. An expression is evaluated on a single machine. And this is, again, not a physical limitation. This is a sort of a logical thing. I want you to think of it that way. But in reality, that's not what happens. And if you think of the expression that we're evaluating, call that a client, it communicates with sites by messages. And all fundamental sites are local to the machine, and our timer is also local to the machine. Concurrent and distributed executions are derived from an expression automatically. I won't show the last part. So this is the last thing. Actually, I should have said that not all 3 combinators. I should have a way of defining expressions, giving them name, and reusing them. So here is the first example. Can anyone tell me what the first one does? Mail 1, say.
Emails differ from the first responder.
Yes. Whatever the first response is, that's the one that's mailed, and that's it. At most, 1 thing is mailed, not 2. Yeah.
What you have between the parentheses there is just CNN vertical bar BBC.
Right.
Is CNN by itself equivalent to CNN open parent close parent?
Yeah. Yeah.
Okay.
Yeah. I mean, I haven't put the open. If there are no parameters, I've just removed the open pattern.
Okay. That is a site call.
That's a site call.
Okay. So given that that's a site call,
Yeah.
how do you CNN itself is not simply a variable name bound to the site.
No. It's a site call. It actually makes a call to the site, and whatever value is returned from that site is a value published by that expression.
Okay. If the value is a channel for a site, that could become M. Okay, so that would be so M is a variable. The identifier CNN is not a variable. Something there's another name.
Yeah, that's why I have put it in capitals.
Okay.
And what does the second one do? That's a harder one. So since you've given a correct answer to the first one, you are the obvious choice to respond to the second one.
Sends the first responder, waits, sends the...
No, it's a little easier if you say that, go back to my previous answer on mail once, and I'll just do mail once over and over.
All right, sends all responders, but with a delay.
Yeah. So first time I try it now, maybe CNN response, that goes out. I'll wait for T units. Let's say T is 1 day. Next day I call them again, maybe BBC responds first now. That response goes out. So every day I'll send one email, either from CNN or BBC. But this whole thing doesn't publish a value. It only sends emails, and you can prove very easily it doesn't publish a value. Ignore the last line, it's a very technical comment, and I don't have time to talk about it.
So, Jay, just for clarity,
Yeah,
with that mail loop thing, if it doesn't get a response from either website, nothing will get mailed. And
exactly.
Okay.
Exactly. And then what will happen?
Wait 2 seconds, or
No, if nothing gets mailed, then mail once will not publish a value. So that's where it ends. Nothing will proceed. It's right here. Yeah. So exercise for you, David. Modify this program. You know.
But Jay, if mail once, after some very long period of time, does publish a value, then
it'll take off from there.
Yes. Okay.
So we've missed 3 days.
Missed 3 days.
But then from then on it will take off. Very good. I mean, I've given this talk many times. Nobody asked me this question, but it's a very good question. Here's a little example that's quite useful. I want to define something called a metronome that publishes a signal every unit. So look at the expression there. And I have drawn a picture, sort of a tree structure that corresponds to this. So the right-hand side has 2 parts to it, separated by the bar, and the 2 parts are evaluated immediately. The first thing that happens, of course, is that signal is a site that responds immediately with a signal, and that's published. But the other one is waiting for 1 time unit. After that, it starts behaving like metronome again, so another signal will be published. And that goes on. And pictorially, the tree shows how the signals are published. R is the R timer, and S is the signal. And of course, we can write a similar program which bounds the number of signals. It publishes only n signals. All right. So for those of you who are constantly watching Google stocks to go down to $20, here is a program that's quite useful. What you would like to do is to call a query side that returns a value. Let's say that the query side returns the current stock value of Google. Anytime you call it, you expect to get that. It might take some time. And then you have a site which checks to see if that value has reached $20 or if it is higher. That side is accept. You give it a value x. It compares x against 20, and if it's lower, then it publishes. Otherwise, it stays silent. So those are 2 sides given to me. What I would like to do then is continuously ask for the value of Google, let's say every hour, and do it forever, and publish all the values, all the points at which the value is below 20. The point is not that it cannot be programmed in any other way, but interestingly, you know that there is a loop there, but the loop isn't explicit. The loop inside metronome, which publishes all the values, that forces a number of threads to start out. Each time metronome publishes a value, that starts one thread to call the query side and call the accept side. Next signal starts another thread. So a whole bunch of threads start out, each doing something at different times. And this I have found to be a very powerful way of doing loops and other such things. Once you have a loop inside one entity, you can use that in others. All right, timeout. Yeah?
So in the previous example, can you get your results back out of order?
Yes.
Okay.
That is quite correct.
All right, and you don't care
And
right now.
typically, in such cases, of course, you will put a timestamp on them. That will put them in order. Yes?
It's not clear to me how you avoid a hang, or how do you loop around this last line there?
Metronome, you see, is guaranteed to publish a signal every unit, right? And if you recall this picture, think of F as the metronome, the top line. Whenever it publishes a value, it creates a copy of the rest of the expression, right? So in the example, yeah, every time it publishes value, let's say every hour, you start the new computation query x accept x. Next hour, another query x accept x. So lots of threads are starting out, and some of them will publish values and some of them may not. And so the question he asked was that if you have a bunch of independent threads, they might publish their answers in different order. That's true. We don't expect them to typically, but they could. Timeout that was raised. So here is the simplest timeout example I could think of. Call a site M and publish its response if it comes before time t. Otherwise, just publish 0. And this is where the where construct is very useful. So run 2 threads, if you like, call M thread and R timer thread. And R timer, if it exhausts the time t, then just output 0. I thought I talked about the site let. Let is an identity function. Whatever the argument is, you just output that. Was it one of the fundamental sites? It should be.
It was on a previous slide.
Yes, I missed that. Let. Whatever you give to it, it comes back. It's identity site.
I'm getting a little anxious about your lack of termination.
Yes.
Why should I not know?
Why should you not what?
Be anxious about the lack of termination semantics.
You shouldn't be. For the first reason, you should trust me. The second one is that in practice, as we find in concurrent programming, most of the time there are threads. Some of the threads are terminated explicitly. Some of the threads are asked to linger for a while and they're terminated after some time. What I'm doing is showing you an idealized model where you don't have to worry about that, and the implementation takes care of the termination.
But I could not formally prove that any of your programs terminated.
No, you cannot prove that. All you will be able to prove is that my programs will show a certain behavior. And that behavior might go on for, say, 10 seconds. And after 10 seconds, in this program, let's say timer t is 10 or something. And after 10 seconds, the behavior continues till infinity without doing anything. That's what you will be able to show. So it's formally terminated after 10 seconds. Yeah.
So it doesn't return a value saying that, hey, like the thing didn't terminate in time. It just kills it pretty much, right?
It kills it. In this particular case, what will happen is that if the timer returns first, we have already asked M to return a value. We can't suspend that. But if the timer has returned first, we'll return that value and the main computation will continue. And M may respond later, but we'll ignore that. You don't seem very convinced.
Well, I'll think about it and then ask you later.
Okay.
But formally, it could have just been killed. You don't care about it thereafter.
No, you don't care. In particular, if you think about it, suppose M is followed by another call to N. Then we'll never call N, right? Because that value will be ignored. Okay, there are special primitives for doing this fork join parallelism. You want to call 2 threads simultaneously or start 2 threads simultaneously, and only when they finish you would like to continue with something. And here's very simple examples. So call M and N in parallel, and only when both return their values, only when both respond, then continue doing something. And you can handle it this way. Let UV, where U comes from M and V comes from N. That's a little new notation I've introduced. It really stands for the things at the bottom. There are 2 where clauses there, but I'll use that notation. So what happens there? You call M and you call N simultaneously, right? Because you start evaluating the big expression, and then that states that you should do that N. And if U comes back with a value, you still can't compute the top line let UV, because not both arguments have been are available. So you wait until both are available, and at that point both m and m have returned. So you can take this expression and concatenate it with some other expression. So in particular, if you look at no, I don't have that example. I was maybe yeah. Suppose you want to do something called barrier synchronization. Look at the line at the top, m followed by f bar n followed by g. So if you run this directly, then you will of course run two independent computations. Suppose you want to synchronize them in the following way. You will call f and g only after both m and n have finished. That's the way to do it. You just fork join let through that and then continue with f and g. Here is an example that shows quite clearly how you can get a lot of power with very few symbols. This is the program that I use to query my students in the class. I want to send, let's say, questions to 50 students, and I would like to count how many of them have responded within a day. So here 10, what am I using here? 10. So 10 time units. Count the number of responses that you receive within 10 time units. And this is very easily done because we can use recursion. So tally, if the list of students is empty, then of course you return the value 0. Otherwise, if the list of students is of the form m followed by a tail ms, then you want to run the tally on ms. And also call the first site and time out after 10 units. So if it returns a value before 10 units, you output a 1. Otherwise, you output a 0. And the whole thing is the value of u plus v. Is that clear? I know it's really brutal to spring these kinds of programs at 5 in the afternoon, but I thought it's a simple program. It's not too difficult. You agree, right? Good, because we have much more difficult programs coming up.
Can we back up on the slide?
Yeah.
Okay. No, you backed up more than one slide.
Okay. Just tell me how.
Forward. I'm sorry, I lost it.
Just tell me what it is.
You were showing the equivalence. You were showing barrier synchronization.
Yeah.
Yes, good. Okay. The second program is not equivalent to the intent of the first program with the barrier because
We're talking about the data transmission?
Yeah.
Yeah. It is equivalent. I didn't explain to you what those double greater than signs mean. It means the same thing as with an x in the middle, except that x part is not used. If x is not used, then this is an abbreviation. And your question is well taken. Suppose x is used, how do you do barrier synchronization? So you take that tuple uv. It gives you a tuple uv. So you feed u into f and v into g.
How do you do that?
You put in that little greater than sign uv, and f mentions only. Yeah. Okay, we did this. Let me not do this. I was trying to show that it has all the power of CCS, like the most important one being arbitration, but I'll skip over this. Let me do this. This is a very interesting one, and it took me some time to actually find the right solution. I want to call a site, but and the site may respond to me quickly or slowly, I don't know, but I don't want to publish its response for 1 day. Why would you like to do a thing like that? Wait, the second bullet will tell you why. But take that as the problem. Just call the site. If it comes too early, wait until the day is over, then publish it. If it comes late, after a day, publish it immediately. Okay, so take a look at that right-hand side. The right-hand side says call n. And at the same time, you are running a timer. If the timer succeeds first, n has not responded, then you are waiting to receive the value from n, and that's published. If, however, n succeeds first, so u has a value, timer is still running. It's waiting until the day passes, and then it publishes it immediately. The reason I like this, you can structure the next problem, which is quite important. You want to call two sites. There are two airlines that I like, and I would like to take the quote from American over Delta if it comes in the next 30 minutes, even though Delta may have responded to me first. I want to give 30-minute interval, and in that time, American can come in any time, and I'll take it. So all these airline names, by the way, are fictitious. They're in no way related to anything. So what you do is you call M and delay at the same time, and whichever value you get, you give that value. So that gives preference to M. And I found it very difficult to write it conventionally, so I thought maybe there is something here. I will not go over this. How do you process interrupts and how you come back, I mean, how you, what's the term, how you process the interrupts and roll back some states. But roughly speaking, here is the problem. That suppose this was in fact one of the problems that motivated me for a long time, and I didn't say a solution. Suppose we have this program running. The goal of the Orc programs are that they're supposed to manage hugely complex transactions and disaster recoveries and 9/11s and these kinds of applications. But outside of this, things can be done by people. So in particular, let's say that we are running a visitor scheduling program in which we have contacted airlines, we have already made reservations in hotels, and we have set up a room, and all kinds of things have been done. And this visitor then gets on the phone and calls me up and says, sorry, I'm not coming to a red state, okay? Just puts on the phone. What has happened at that moment is that I should somehow interrupt this expression, evaluation. I should roll back whatever has been done. But you can't do that. You say there is nothing in the semantics that says you can cut it off. So the solution, I realized, is that you anticipate being interrupted, and you set up a site called interrupt. And when you start executing or evaluating F, you also evaluate interrupt. And if you do get an interrupt, you cut off F, because that's the mechanism that's available to us. So the telephone call actually sets the interrupt, and only then the interrupt side will respond to the get. But of course, you can have many different codes for interrupts, many possible interrupts. And the particular advantage of doing this automatically is to find out how to roll back. Consider a computer company that has an order to build a computer like Dell, and it has already contacted with vendors, and it has already gotten commitments for parts. And then the customer says, I don't want a computer. So you have to roll back. You have to redo certain things, and you can put in the policies as part of the Orc expression. Yes. Okay. Anyone who can answer this without looking at the solution will get something from me. The quarters that I haven't used at the parking meter, something like that. This is a truly important example. It's the essence of many things that we do on the web. The essence is the following. We want to compute OR of two Boolean values. There are two sites. I would like to call them simultaneously, and I expect them to return Booleans. But of course, they're asynchronous. I don't know when they will come. If I get a true from either of them, I would like to publish the answer as true, independent of the other site. But if I get a false, I'll have to wait until I get both falses, and then I'll publish a false. Why it is important is that this is exactly the same problem in the airline quotes. You get a value which is less than 300, you want to take it. So this is the essence of the problem, and that's the solution I wrote. If true, for a Boolean, says that publish true if the argument is true, and don't do anything if the argument is not true. So that is the same as if, except that it has to publish a value true or not respond. So the top line says you publish the value from x if it is true, publish the value from y if it's true, or call the site OR with xy and get the value. And at the same time, you run m and n. So let's say m responds with true, so that if true x will immediately produce a true, publish a true. Is that clear? How many values can be published potentially by the top solution?
2?
3.
3?
If both x, y are true, then all of them will publish true, right? All 3 of those alternatives will publish true. So we can get rid of that. We can say we'll publish just one value by the second solution. That kills the computation once a value is published, right? So the way it is related to the airline quotes problem is that it has exactly the same structure. Threshold returns the value if it is less than a certain $300. C stands for 300. And min returns the minimum of x and y. So call the airlines A and B and publish one of those 3 things and do it as soon as possible. I won't show this to you. By the way, I was giving this talk last month at MIT, and Richard Stallman, you know, the GNU person, he said that I must announce in any talk that I give that if you would like to write software on this, software for this, or software about this, you should contact him and publish it under GNU license or something. So it was totally confusing that I didn't understand. I just asked my collaborator to talk to him, and so yes, the bottom line is this: yes, do some programming and publish it, and don't try to make any money. For those of you who are aware of the difference between angelic and demonic non-determinism, I found that the 2 constructs in this language exemplify these 2 different kinds of non-determinism very nicely, and you could exploit them in programming. And I will give you one example. So angelic means it's the automata theory kind of non-determinism. You have a tree structure typically, and you are looking for the existence of a path that leads to a good state. So you would like to answer the question, does there exist a path satisfying something? And demonic says that it's entirely possible we'll take one of the paths, so make sure that every path we take is leading to a good state. So typically in programming part we do demonic, whereas in automata theory it's a lot easier to do angelic. And I found that if you combine them, you get a lot of power. And I'll give you one example of that. This is a fun problem. You won't solve any big web services problem with this. Think of the 8 queens. You all know the 8 queens problem, right? You can depict it as a tree, and when I put a red cross, it means that that's not a feasible solution. We cross it out and don't expand it any further. And typically, we on a sequential machine, we do backtrack searching. And then I searched on the web, and apparently hundreds of solutions have been given for this problem in many different languages. You go, there is a reference in my paper to the paper which says 100 solutions or 114 solutions in different languages. But you are lucky to be here to see the best solution. Okay, the best solution is given in these 2 lines. This is it. I'm not exaggerating. I haven't seen anything as good as this. The idea is the following. Let's say that you have a partial solution x that I'll call x, which is the placement of queens on some of the rows of the board. I have an expression called extend that extends that solution by some number of queens. The next argument there, extend z n, says take the solution z and add n more queens to it and n more different rows and give me a good solution. And the way it works, extend z with one argument is take z, and in the next row try to put a queen in position 0, try to put a queen in position 1, take all of them, all 8 of those possibilities, and do a bar. So valid is a site which, given a particular configuration, will check and see if it's a valid configuration. If it is valid, it will return that configuration as the value. If it is invalid, it's silent. Therefore, if you try all 8 things, maybe 5 of them succeeded. They're valid. The remaining 3 are not valid. So that is extension by one queen. That part is simple. And how do you extend by n queens? Well, one by one. So the last line tells you how to do that. You extend by one queen. And then for each of those solutions, you extend them by n minus 1 queens. Remember the piping operator? For every value published by extend z1, it will create a new copy and create n minus 1. So this is exactly what a backtracking solution will do, or a tree solution will do. This is total angelic non-determinism. We're not cutting off anything except where we know it's not going to work. And the original problem is solved by calling extend with an empty board and extend it by 8 queens. If you have seen a better solution, well, I'm being totally immodest here. If you have seen a better solution, please let me know so that I can curb my immodesty next time. Yes.
How hard would it be to write like really fast solutions that do caching and take like advantage of other stuff in this language?
Well, caching, of course, you are at the mercy of the implementation. But this one runs in the typical fashion. It actually does exactly the same amount of work that a backtracking search will do. The only difference is in a backtracking search, you may look for one solution only. You don't care about all solutions. This will give you all solutions.
But there's certain solutions to the any problem, if I recall correctly, which do really smart like pruning off of different sections of the stuff.
I don't know any special way of pruning that you can do.
Okay, all right.
I mean, there is no theory about it. There isn't any particular mathematics. Well, the next question, let's see. Do we have some? Yeah, we do have some time. Would you like to ask some questions? Are you bored? Should we stop?
No. I have a question.
That's how I'm a popular
Can you
I give them options.
can you implement the parallel OR sequentially?
I'm sorry?
Can you implement the parallel OR as on a sequential machine just by doing each process sequentially?
Yes, you can. In fact, the implementation that we have right now is sequential. It's on one machine. It keeps track of the threads, and it keeps a list of the timers that are waiting. So it is totally sequential.
Right.
There is no distributed implementation. Of well, it can be done in distributed fashion, but it doesn't have to be. Well, as you have seen, even though I started out talking about web services, there is nothing that says anywhere anything about the web. You can take any application and you can divide your application into what you call sites, which are the primitive operators that keep track of data structures and that modify, that sort and add numbers and such things. And then the control logic could be written in this language. So one of the questions that comes up then, can you do all kinds of distributed programming in this style? And that was really my intent. I have worked for a long time in this area with some of my brighter students over there in the back. The point was, how do I treat a process? I mean, isn't a process something that's always waiting to receive some input and then you do things? In this language, I don't have any notion of waiting for inputs. It starts out evaluating. Well, the answer is very simple. The answer is that just like your home machine, what you do on the home machine is that you receive email. The machine is not waiting to receive email. It has to request some kind of a mailbox to give it email. And that's what the thing is. When you start up your machine, you start evaluating something. And that's the same trick we'll use here. Take a typical iterative process. It reads a value from a channel. It computes with that value. It writes the computed answer to another channel. And then it repeats the process. So I have given a name there. The two channel names C and E are parameters. And C.get is a site call that gives me the next item from channel C. And we call that item X. We compute with X, and we output that thing, and then we go back and recompute. That's typical. And if you want to build a network, that's very easily done. You want to put two processes. They read from different channels, but they write to the same output channel. Then you do PC and PD, then that will work fine. And here is a typical kind of computation that we do with processes. Let's say that a child is playing with a computer, and the child puts on a particular channel a number. The computer figures out if it's a prime number, and if it is, it outputs true, otherwise false, and then the child then goes back to putting another number. As you can see in the last part, you get the number from channel P from the child, then compute, call a site prime to find out if it's prime, and then output the answer, true or false, onto another channel, and then go back and run this computation again. So you can write the usual kinds of things that you can do with processes, but also you can do things that you haven't typically done with processes. Like if you take Byzantine algorithms, they needed to be synchronized every round. There is a notion of a round. They compute, they receive data from others, they compute, and they send something, and they all wait, and that's one round. Such computations can be very easily written here, because we have the facility, as you can see, with fork join parallelism, to create the notion of a round. So I've given a lot of examples, and it might seem that, yes, this is powerful, but it's really, this is what motivated me in the beginning, that there is a notion, there is an algebra called Kleene algebra. Some of you may have seen it under the name Algebra of Regular Expressions. And these are some of the laws in Kleene algebra. I have changed some of the laws here to suit Orc for left unit and right unit of this. So in particular, if you look at commutativity of bar, f bar g is g bar f. These are some of the laws I would like to be true for my system. But the way I have described the system so far, there is no way of proving it. The description has been totally hand-waving. This is what it means, because I wrote down in English what it means. And it's true, and it turns out that not all these laws are true. In particular, if you take f bar f, that's not f, because you are starting two computations of f. That's not starting one computation. So you call CNN bar CNN. That's not same as CNN. You're making two. Oh, you make two calls to CNN.
I know, but for the thing that receives it, it can't tell.
It can't tell which one came first, which one came second,
That's
but it
right.
got two copies, and it might send two answers back, and you'll publish two things.
But it might have gotten two answers anyhow.
No, it
You
would.
don't know.
Every side call elicits at most one answer. So
Or if you receive two, then it's different, and you can tell it's different.
yes, what I'm saying is that it's not guaranteed to be the same. That's the point. That f bar f is not guaranteed to be the same as f. Or f followed by 0 is not 0. You do something in f and then say, I don't want to do anything more. It's not same as not doing anything at all. Or the last one, that's much harder, left distributivity. Let me see if I have a picture of that. No, I don't have a picture. What it says that you call f, and whatever answer you get, you start g and h. That's one way of doing it. The second possibility is you call f. The left side, whatever answer you get, you do g with that, and for right side, you do h with that. The two are not the same, because the first one, g and h will be started up with the same value, definitely, because f will give one answer. In the second case, f might give two different answers. The point, though, is how do you prove such things? There's no way to prove this with whatever machinery I have given you so far. So we need a real semantics. And I must confess, and there are some additional laws, I must confess that from day one, the semantics was very clear in my head. And till day n, I could not explain it to anyone. You could give the hand-waving stuff, but then people like Shankar would come up and say, well, could this happen? And then someone will say, no, that can't happen. Then someone will say, yes, it could happen. And in fact, in my own class, I have been able to prove laws which were not true, because it was all hand-waving. So what we found was a very nice way of writing the semantics, and this is really quite powerful. Let me actually put one large one up. This is the entire semantics for the asynchronous model, where time is not involved. And when time is involved, there is a similar one, but it extends with time. Let me explain to you very quickly. At 5:20, we don't explain semantics. But let me try just one. When I write f, little arrow with an a, f prime, it means if f is an expression, it can possibly engage in event A and become a new expression f prime. And the events, there are only 4 kinds. There is a site call event, there is a receiving a response event, and publishing a value event, or there is an internal event that no one can see. It's called tau, typically. It's called a silent event. So if you look at, say, halfway down on the left, will the mouse show up here? Yeah, this one. It says that if f can engage in event A and become f prime, then f bar g can also engage in that event and become f prime bar g. And there is a similar law just below it for g, and these 2 laws give the semantics of f bar g. And given these 2 laws, you can prove that bar is commutative. F bar g is same as g bar f. You can prove that it's associative. You can prove that f bar 0 is same as f. Yes, it takes a little work, but yes, you can prove it. Associativity you can prove. Is that a question?
Commutativity, for example, the order of the outputs from f bar g.
Yeah.
I mean, from looking at that, I can't tell
which one published it.
Well, in particular, if the actual semantics of f bar g was that all the outputs from f were tagged as being on the left and all the outputs from g were tagged as being on the right, then it wouldn't be commutative, but the 2 laws that you wrote there still holds.
Well, the same tagging will apply, right? F will name itself.
No, I'm saying if f bar g would not be the same as g bar f.
Well, how do you say that it's coming on the left? F can only say its own name. It will say this output is from f. It cannot say that this output is from the left side, because f doesn't know.
What the bar operator was doing, for example, the bar operator was ordering all of the outputs from f as having come before all the outputs from g.
It doesn't do that.
Well, it doesn't, but you can't tell that it doesn't do it from those 2 laws.
No, I certainly can, because I can show you one particular example in which it doesn't, right? Maybe I'm not understanding what's bothering me.
You're saying that the 2 laws imply that the bar operator is commutative.
Or you can prove from there that bar operator is
right. And I'm saying that those 2 laws don't say anything about what the form of output is from the composition.
Right.
And if the form of output from the composition is asymmetric, then the...
No, it cannot be asymmetric. That's what they're saying.
How do those 2 laws tell me that the output cannot be asymmetric?
All right, let me go to the next part and sort of... Yeah, do you have a question?
Oh, I was thinking that I think the question is that you never define the vertical bar, right? That the bar is never.
That's it. That's the definition of vertical bar.
What?
That is the definition. Those 2 laws are the definition of vertical bar. Yeah. So if I give you, let's do one example. Before I go off, let's do one example. Yeah.
There's a pad and a pen over on the side there, and
no. I have thought about this. Here's an example. So take the expression at the top, and on the left side, I show some of the events that happen, and how that expression gets transformed, right? So if you look at the first expression, it says that the S, there was a colon S, colon site S. That's the first thing that happened, and we give a subscript k to identify which call it is to S. There may be many calls, so k tells us which call. That's an event, and then that expression gets transformed to this expression where S is replaced by waiting for the response to k. This question mark k means we're waiting for the response to k. Now this part says we call on n, and again I put a subscript L. So this gets converted to waiting for the response to n. So this is the expression we have now that we are evaluating after those 2 events have happened. Now let's say that we did receive a response to L, which is value 5. when that happens, this L gets converted to let 5. That's one of the rules that tells us. Okay? And this remains as is. What happens in the, so we have this expression, and now we would like to put that value 5 into x and reevaluate this whole thing. Okay? And that's what happens. We put that value 5 into this, so mx becomes m5, let x becomes let 5, this y remains, this ry remains, but we kill off this part. We don't do any more of this. Okay? And now this is quite quite independent which of these two we're going to do next. Right? That probably go towards answering some of the things.
Could you go back to the slide with all the laws?
Yeah.
I think I'm going to take my question offline.
Okay. The interesting part of these two laws, this particular law is very interesting. Yeah.
The possible answer to that is that although he can define f bar g as enforcing an order that the result from f comes first, that nobody else can tell.
No, yeah, you cannot, I mean, a bar cannot enforce that. That's exactly it. With this definition, there is no way to enforce that. Yeah.
You know, from any other expression. Right.
Well, he's saying that let's tag it with the values from f. But f doesn't know which part of that expression it will be embedded in. It doesn't know if it is going to be on the left side or the right
So
side.
I'm not saying that f does the tagging. I'm saying the vertical bar. I'm saying that let's say the vertical bar was tagging all of the things, or treating the things that came from its left side differently than things that came from its right side.
Right.
And in the example you went through,
Right.
there was the substitution through the let by which the thing came out.
Okay. Let me take this offline.
Yes.
You'll quite right. So there are only about 4 minutes, so I don't need to go into this. But let me give you the rough idea of how do we do these things. We use what is known as bisimulation to prove these laws. Strong bisimulation will work for these. And then there are a large number of facts that we found to be true about Orc that are not true of other process calculi. The combinators happen to have all the nice properties that you see in functional programming. They're monotonic, they're continuous, even though we are dealing with a system which is highly non-deterministic. So what happens as a result of that, the bottom line is that when you have a recursive definition like this is the metronome example. I have simplified the notation S, R, and M. What it really amounts to is that you have an infinite chain of expressions, M0, M1, M2. M0 is 0, and M1 or Mi plus 1 is derived with Mi on the right side. And the limit of that chain is that M. So all the nice properties that we can think of, denotational semantics and everything apply to it. So I'm very encouraged. But at the same time, I know that time requires a much harsher treatment. And we have the theory, but we haven't tried to prove similar laws yet. So if any of you would like to work on this, please contact me. We would like a lot of software. We would like a lot of theory. Or if there are any mistakes, we wouldn't like to hear about them. Thank you very much.
We still have time for questions. You want to go on just a little bit further?
Is there an implementation?
Yes, there is an implementation. Do you know how fast, Google has a spell service. You give it a word, it gives you the next word. Do you know how fast it works? 13.6 times per minute. That's the kind of thing we have been able to do with the implementation. It's a basic implementation, and it doesn't have some of the things that I want, like a library of sites, and its communication with the actual sites. American Airlines is still very primitive. But we have been able to do a few things. Yes?
I've asked lots. If anybody else,
You will use this. Okay, there's no one else.
okay, we'll just kind of program this algorithm. But I'm concerned about the semantics of the where construct regarding site calls. If I call CNN and BBC, is it the case, if I say where, and then I call the two of them inside, yeah. Are you guaranteeing that only one gets called?
No, I'm guaranteeing that both get called.
Okay,
I'm guaranteeing, yes.
So what gets terminated
when we receive a value from either of them?
Yes.
We terminate. And of course, in this case, termination means we can't do it for BBC, which has been called. So when we receive, if we do receive a response from BBC, we'll ignore it.
Okay. So under what circumstances are you guaranteeing that calls don't get made because a response has been returned?
Where did you say the pad was?
It's over on the other side of the computer. And there should be a pen there as well.
Between
on
the
other side.
On the other side, or large.
Between.
Oh, this one.
Between the monitor.
Oh, yes, yes.
Hoping they bring, yes, they bring us.
Okay.
Just leave it out.
When you put it down, we can see it better.
Table.
Then we get out. Look behind you.
Turn around and see the screen. You see?
Good. Suppose we receive the response from R first. Right? We haven't received the response from M yet. I can guarantee that N will not be called. Because when we do receive the response from M, we'll ignore that, and therefore M will not be called. It is possible that we receive the response from M first, then we'll call M. And so M and R both have been called. And let's say R response, we receive R's response, then we'll take that. We can't undo the call to M, but we will ignore that.
But Jay, don't you make a call to both N and R, and then take the first response?
Both M and R, yes. That's what happens first. And that's what I said, yes.
But wouldn't you also have called N, and then take the first response?
After M returns a value.
After M returns a value, you take whichever value, you call both N and R.
No.
No?
Precedent.
Yeah. That's your precedent. Okay. So there is serialization.
Can you talk more about interrupts? I'm just curious. It's like, I don't know, if something did get interrupted, do you just not handle anything at all? Or is there a way that's built into
No, I mean, you can program the whole thing, that you can handle the interrupt at any level that you like. You'll have to look at the structure of the expression. Say, yes, I made a hotel reservation, I must cancel it. Or airline reservation. So it depends on the structure of it.
Okay.
You might want to roll back to some previous state. Yes, that can all be done. You might get an interrupt code from the interrupt. There are three possible interrupts. For the first interrupt, you don't do anything. For the second one, you roll back in a certain way.
But I can implement this sequentially, right? I can
Yes.
execute M and
Yes, exactly.
And then
Exactly. That's the implementation we have right now. It's I found the implementation not to be trivial, not at all to be trivial. And quite surprisingly, my collaborator, William Cook, who has a lot of experience, he looked at PyCalculus and he got his intuition from there. And I looked at these expressions as expressions in Kleene algebra, or regular expressions. So they're equivalent to finite state machines. So I created finite state machines out of them. And I said that, well, we'll have some threads over finite state machines, many tokens at different places in the finite state machine. And it turned out, when we compared nodes, that they were exactly identical implementations. I had put something on edges, he was putting something on nodes, but they were exactly identical. And of course, William is a tremendous implementer. So he wrote the entire implementation in one day, 1,200 lines of Java. There was one error. So we went over that code and found one error, minor error, but still, that's it. It's been running, but it should be enhanced. Works quite well. Yes.
How would you compare R to the other existing the alternatives?
Better. Okay, I can go into a long answer, but the thing is, PyCalculus has a tremendous amount of theory behind it, which has been built up over the last 10 years. And it's very impressive. I'm very impressed with it, and Orc doesn't have it. You can't claim that this is better than that unless you have a vast amount of evidence. It's just not possible to get that evidence. The only way we can compare is that on particular applications, how well did we succeed in doing certain things. So one class of applications is what are known as workflow applications, like the visitor schedule I was talking about. And recently we started looking into that, and we found that there are some published 29 or so different schemes that they would like to have in workflow. And they're quite difficult. And actually most commercial workflow languages implement about half of them. So we found that we can do all 29 in all. And they're not very hard at all. They're like small programs. We published a paper on that. And PyCalculus, I'm sure, can do the same thing. In fact, we have a translation showing that anything we can do in OR can be done in PyCalculus. We do not have a reverse translation, but I suspect it is true. One of my students is working on it to show that anything that can be done in PyCalculus can be done in OR. But that's not the important criteria. The important thing is which is useful. PyCalculus has many other virtues. Most people now apply it in the security arena, believing that whatever an attacker can do can be expressed in PyCalculus. So that's the limit. That's taken to be an axiom. And I don't have anything like that. But I have a feeling that it's a little easier to program it.
So what really was your motivation? I mean, did you start this because you felt something else was problem was not solvable in another language?
They were being solved, but they're much too difficult. Actually, I worked on this very hard for several years, for 3 years. And I produced a number of very bad papers. And then I suddenly saw the solution in 10 minutes. And I knew this is what I was. Thank you.
So I think we're finished. I'm sure that Jay will stand around and talk afterwards here. Thank you very much, Jay. It's very interesting.
For information on other online Stanford seminars and courses, please visit study.stanford.edu.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.